Okay, so where we ended last week, we ended with Zaitsev's rule. Okay, I believe is what we ended with, which now gets us into the E2 kind of repercussions, so visualizations behind this. In the E1, the end product we get tends to be just the trans, because that's the most stable. And since we form that carbocation, we can get free rotations, all that kind of fun stuff, to align us to the trans product primarily. The E2 is much more structure dependent, or much more kind of transition state dependent, which kind of makes sense because we only have reactants and products, which means in the E2, in one step, it's all going to depend on what's happening in that transition state, right? So when we're looking at a reaction that we think is E2, we need to be careful to make sure we have that proper alignment. Right? So Cardi did a pretty solid job on picking these two examples. We should immediately kind of freak out when we look at these because what jumps out of the page at you? The benzene rings, like jumping out of the page or jumping into the page because we have stereochemistry. Okay, it's that stereochemistry that we're going to have to watch out for and be very cognizant of when we go through and do the E2. Just like we do the SN2, we have to be careful that when we run that reaction that we're paying attention to how that stereochemistry aligns. Okay? In the E2, what's happening mechanistically? Okay, we're making a double bond. Remember, as we talked about with our eliminations, I would argue that that's a good thing to focus on beginning to end for a reaction. That's not a good thing to focus on when we think about our mechanistic steps. Okay, because that formation of the pi bond is kind of gray area-ish on a making of a step.
I was just going to say that they happen at the same time.
They happen at the same time. That's good. What is they?
Two atoms or two leaving groups.
Okay.
Sorry, not leaving groups.
There's not two leaving groups. Okay, but the two sigma bonds, when we run an elimination, as Christian was suggesting, this formation of the pi bond through breaking two sigma bonds. Okay, those two sigma bonds are not both leaving groups. That is a common statement to make. They aren't leaving groups. A leaving group literally leaves the structure with electrons. Okay? And all of that has to do with how we talk about OChem. OChem is all about electron motion. So a leaving group leaves with electrons. Okay? So we could go through and look at this. We have our leaving group, the bromide, leaving with electrons. Okay? Because this is an elimination, that second sigma bond also has to be broken. That second sigma bond is to that hydrogen. Okay, why that hydrogen and none of the others? And by others, that was vague. Why not say this red methyl or this green phenyl? Okay, it has to do with the reactivity. What do you got, David?
You've got two beta positions, and that's the only beta position.
So that's going back to the hydrogens, and that's not what I'm asking about. If we compare the red methyl and the green phenyl, okay, why did those not get broken off instead? Okay, we could make them anti. Okay, it has to do with how can we quickly stabilize that piece. Okay, that hydrogen to break off has to come off as H plus. How do I stabilize that positively charged atom? If the methyl did that, that would be a positively charged carbon. That would be a zero-area carbocation. Is that stable? No. If the phenyl did it, that's larger. We cannot form carbocations on a phenyl ring. It doesn't happen. Can I stabilize any of those three groups? Okay, H plus, C plus, phenyl plus. Which of those could I stabilize the easiest? Well, H plus matches the description of an acid, which means how could I stabilize that quickly? I could add a strong base. I know it is strong because it is negatively charged. That negatively charged base can come in, attack the hydrogen atom. It's now sharing electrons with that hydrogen. The hydrogen now exceeds its octet, so we break a sigma bond, and in the result, make a pi bond. Because this is now happening all at the same instant, we're forming our pi bond. There it is. Right? The same time that phenyl is wedged upwards, I'm going to stop writing it as that ring, just our pH. What happens at the other position? Well, I still have that methyl, CH3, and I still have that phenyl dashed. Okay? This representation is an awful drawing because this doesn't accurately show the three-dimensional characteristics. Right? Because I know each of those carbons is now sp2 hybridized, I should be better representing this in its flat structure. Okay? So what I'm doing is taking that weird twisted structure that's kind of coming in and out of the plane at you, and I'm going to pull those front phenols and I'm going to rotate them down. Okay? So in that case, anything that is wedged comes downwards. So on the right-hand side, that would be a phenyl. On the left-hand side, I have the methyl. What is dashed on the right-hand side?
Hydrogen.
There's a hydrogen back there. The bromine has already been removed from the structure. There's an implied hydrogen hiding back there. What's the dashed on the other side? The phenyl. The end result of that top reaction is that I end with this blue structure. Notice, I don't know why, well, I do know why I meant to did that. Those shouldn't be dashes, those should be solids. Okay? The end result is I have this nice pretty picture from all of that complex stuff going on. Okay? That's what we're aiming for, that's what we're trying to get towards. Okay? That thing in red can be useful for us as work to show us how to get there. Right? But it's going to be exceedingly rare for anybody to actually show that as valid work to get any points for it. Okay? You're not going to see that as a multiple choice answer. Does that make sense? Okay? So what I'm going to go ahead and do is erase the red work. I'm going to redraw that blue structure. And while I'm doing that, you should draw the product of the bottom reaction. Everybody get it drawn? Right. When we look at blue versus purple, what is their relationship?
One is cis, one is trans.
One is cis, one is trans. They're geometric isomers. Okay. If we go back and look at the starting materials, okay, we had the same base. I just want to notice this. Note where I drew the base. Right on the back side where that hydrogen was, right? To set that up. Where did they draw the base?
On the other side.
On the other side of the structure. Why'd they draw it on the other side of the structure?
Because that's how you write a chemical formula.
We typically start with our largest organic materials and almost always work smaller. Okay? Unfortunately, that organization is not conducive to our mechanisms. Okay? So if you're going to try and draw out a mechanism, you may end up needing to draw some really goofy, gangly, long arrow to set it up. Okay? Or you redraw that strong base. Okay? What is the relationship between those starting materials? They're diastereomers. Right? How many people looked at it and were like, yep, that was diastereomer immediately? Yeah, okay. See, this is why this becomes challenging. Okay? Because I'm going to add to that I'm going to bet those people that said, yes, those were diastereomers, probably saw that pretty quickly because there were two structures. If we only draw one, guess what both answers show up as multiple choice? Both of those. Does that now become an easy question to align? No, it's only easy if you slowly break down each of those pieces and draw in that extra work to see that alignment. Right? Because we can stack this and make it even worse. What is the starting material for the purple compound? Right? You now have to reverse the direction of that reaction to set up that alignment to make sure that all of those things are aligned appropriately. Yes, that is challenging and we have to be careful with it. Yes?
Are questions like that going to be on the test or on the final?
Final, absolutely.
Okay.
Yes. On the test, all I can say to that is you're responsible for it.
Okay.
Okay? That is a much more advanced question, which is the other part of this. Okay? I'm almost always going to say you're responsible for it. Okay? Because you are. Okay? But that is a more advanced question. Would I give you an exam full of those? No. Okay? You're going to get varying levels of difficulty all the way through. Some of them very straightforward, some of them that require a lot of kind of mental manipulations. Okay? Shall we look at that starting material 1 again? If I was to draw the starting material, okay, from an E2 elimination. So if I'm asking you to think backwards, in that E2, I had to break 2 things off of this structure. What did I break off?
A bromine and
A hydrogen and a leaving group. Right, those had to be somehow removed in this structure. Okay, which means if I'm going to think backwards, what do I need to put on this structure?
hydrogen.
A leaving group and a hydrogen. Where do I place them?
On one on either end.
Okay, so pause. I saw your face and I'm going to take advantage of it. Okay, because you're giving me this face of like, God, there's no way I would possibly know that. Could this possibly be right? Would it make sense to do that? Oop, there's the bromine. I was hoping for a little bit of a faster response there. What reaction did we do? You were told you did what reaction to get that purple product?
An elimination.
You were told that you did an elimination reaction. An elimination reaction results in what? A pi bond. So if we're thinking backwards, what's the very first thing we need to do? Get rid of the pi bond. Does it make any sense to remove a hydrogen and put bromine there? No, because that has nothing to do with the pi bond. Okay? And this is an all too common thing that I've had multiple conversations with people about. Zero in on where the chemistry is. It's okay. It's stressful to deal with this. Zero in on where the chemistry is. Once you've identified it, you should mark it. Okay? Admittedly, I screwed up. I said the hydrogen in the leaving group, but we also knew other information. We knew it was an elimination, which means, so I'm going this way, I need to add a hydrogen in a leaving group, and what else needs to happen? I need to remove the pi bond. Okay? If I remove that pi bond, am I touching the CH3? No. So should you? No. Where should the hydrogen and the leaving group go?
One on either side of the pi bond.
Remember, the pi bond is where the chemistry was. How many carbons are in a pi bond? Not David. 2. What things are we trying to add to this? Hydrogen in a leaving group. Which means 2 things. There's 2 carbons, 2 things. What should we do? Put those 2 things on those carbons. Okay? So I'm going to put the bromine here and the hydrogen here. Yes? Okay, you're shaking your heads. Why are you shaking your heads?
Bromine is large, so it couldn't come between the phenol and the methyl because of steric hindrance.
So there could be a steric hindrance argument, which could make this reaction a little bit harder to run. In this case, ultimately, that's not going to matter. Our strong base will remove our hydrogen. We'll get the elimination. A tertiary halide is actually more favorable for an E2 reaction. Okay, so not a bad idea. That might slow the reaction down because of sterics, but there's another really big issue.
The available electrons on the left and right side instead of like on the other side.
When we run our reaction, the bromine leaves, and then what has to replace it? Electrons from a hydrogen. Which hydrogen?
Beta.
Okay, how many beta hydrogens do I have here? 2, which means how many possible hydrogens could get removed to make my pi bond? 2, which means how many products do I get? 2. Both of those hydrogens could possibly come off. Why is that a problem? How many products am I making? Just 1. Did I place the hydrogen in the bromine correctly? No. So I guessed I was wrong. Oh, I give up. No. What should we do? Swap them. Okay? It is okay to guess and check. But the hardest part in that is you must check. And if you don't go back and check that, you run into a situation where you could potentially be wrong. This is literally a 50-50. Okay? And the more I teach chemistry, the more I see that almost everything we've asked from beginning of 130 all the way through biochem, because I've taught the whole sequence, they're 50-50 switches. Okay? It's just a question of how many 50-50 questions we string into it. Okay? So you have to stepwise each question. Should I place here? What would that mean? Ah, damn it. Should I place here? What would that mean? Ah, damn it. Should I place here? Oh, look at that. It worked. You have to constantly be cycling back to see that step. Okay? Otherwise, it's a crap ton of practice. Okay? So you have to have a process for continuing to check and do things, or you've done so much practice that you hope the questions you see on the test are your practice. Okay? Kind of make sense? Yeah. Okay, what do you got?
I have a question about the E2. It says it only produces one product, but if you had something like the, were to switch back to the original spot, which is 2 hydrogens, you could pull off.
And so this is where it becomes a little bit challenging. It can only produce one product. And the can becomes an operative word because it requires that we have a hydrogen that is anti to it. And in that E2 step, one product. But if I switch the hydrogen and the bromine, are there 2 possible hydrogens to remove? Yes. So how many E2s are there? 2 E2 pathways for the same structure. Okay. So each E2 still only produces one product, but I get the option of 2 results. Nope. Nope. Okay. So we do have to be cognizant of that in the E2. The next layer of difficulty that smacks us with this one, or here, let's actually pause on that. What we've now drawn is a basic structure. We can use this basic structure to rule out multiple choice answers, because guess which multiple choice answer was probably on there? The one with the hydrogen and the bromine switched. You can now eliminate that answer. Okay? Take advantage of your multiple choice to help you through this. Okay? The next layer of difficulty would then come in the next question. What becomes complicated about this structure that we've drawn? There are 2 chiral centers. Because I know the hydrogen and the bromine must be anti to each other to allow for the elimination to occur, I have to make sure that that stereochemistry is absolutely correct. How many of you feel you could draw that structure really easily? Ooh. I wonder if there was another way that we could approach that. You're like, but there isn't, dude. We just got to do it. Is it possible that the answer was actually already on the test? If it's a multiple choice, it's more than a possibility. It is. Once I've acknowledged the basic alignment behind those, what could I now go through and do? Just read out the answers and say which one of those has the right alignment for the elimination to happen. And we can now get our answer. Okay? There is a complication with that. What can you tell me about this magic bond right there? It can freely rotate. So the drawing may not actually show it in the proper alignment to do the elimination. You may actually have to go through and do a sigma rotation to align all those pieces to see how it all snaps out. Okay? Would that be an incredibly difficult question? Yes. Can you fully expect to see a question like that on the ACS? Hands down, absolutely. Okay? Yes.
I don't know. You could just kind of like do the elimination, couldn't you?
On the answer choices.
Like you just run an elimination reaction on, because I mean, if you give, like say we get the multiple choice, you have like the one where the
Yes.
hydrogen swap, the one with the
And to make that go faster, if you're asked to provide the starting material, acknowledge what kind of reaction it is. Once you know the reaction it is, start compiling what you know about that reaction. Okay, which is exactly what we did. It's an elimination, which means I have to make a pi bond. Okay, so if I'm going to go backwards, what must I do? Remove it. Okay, hydrogen in the leaving group. Okay, add those pieces of information into a skeleton structure. From that skeleton structure, you now have a home camp that you can start to root out answers to get you to that. Okay? Arguably, even if it wasn't multiple choice, okay? Because there's lots of people that may even watch this video at home and be like, well, multiple choice doesn't test critical thinking. Mother effer, yeah, it does. Because what would you be expected to do even if you didn't have those answer choices?
do the back.
You're still going through that exact same process. You're now drawing those results. You're now laying the wedges and dashes on it instead of somebody else setting that up for you. Okay? You still have to reason through those exact same solutions. Okay? So use that information. It's just a little bit of a shortcut for you so that you don't have to work as hard. Okay? It's still a hard question. Amber.
When you were originally deciding where to put the hydrogen and the bromine, could you start out with a skeleton structure of the bromine in the correct place using the assumption that you wouldn't want the three biggest groups on one carbon?
That was Leslie's argument, and it doesn't really hold water, unfortunately.
Okay.
Yeah. If anything, we want the leaving group there because that's going to support a more stable double bond.
Okay.
Okay, because we know that position would hold true.
All right.
Yeah. Okay? So when we go through and do the eliminations, we have to be very careful for the E2 that we have that anti-alignment. We needed that anti-alignment in the E1 as well. It became a much smaller issue in the E1 because the leaving group leaves first, leaving behind a carbocation. And the carbocation can be attacked with electrons from either above or below. Right? So the relative orientation of the hydrogen, as long as it was in the plane of the pi system, we're okay. Okay? But that alignment was still true there. Okay? So the E2 does have this really big issue with our stereochemistry. We can push this all the way out into Newman projections to see those alignments. We have to have that perfect alignment for them to, eliminate. Okay? If we took a look at that starting material, it was drawn in the anti. If I go through and start to do rotations, you'll notice that I'd end up with other Newman projections where they're Gauss to each other. Those Gauss interactions won't allow for the elimination to occur because the electrons don't align in the proper space, which means the elimination doesn't happen in those cases. Okay? So if we were to draw the E1, it's not as big of a deal because carbocation, I can then do rotations all I want in the back, and it's not really changing the energetics. Okay? So, can you get a mixture of products in the E2? Yes. An E2 mechanism still only produces one product, so how do I get two? What's different about this structure? Where's my leaving group? There's my leaving group. Our other name for elimination was a beta elimination. Why do I get two products? I have two hydrogens at the beta position, which is getting to kind of David's question earlier. There are two hydrogens to choose from, which means, depending on the rotation, I can get two possible elimination reactions. Each of those elimination reactions is going to produce one product. Okay, but those are two distinctly different products. Okay? In the case of those, which one would I prefer? I'd prefer the trans because that's the lowest energy. Okay? So just like the E1, if we have multiple hydrogens to remove, the E2 will get you a mixture of products. It's still going to largely favor the trans product.
Because even when you do the rotation, you can kind of look at that and see it's going to be more stable. It not only is the trans product going to be more stable, it's also going to be more stable in the reactant in a position that makes the trans more likely to happen.
Yes, the Newman projection. Yeah, that's exactly why. It is that. Yeah. That's what's forcing it. Okay? So, really what we've covered is kind of a massive blend of both 8 and 9. I have a hard time distinguishing the way Cardi does the content from Chapter 8 and Chapter 9. But kind of for the most part, Chapter 8 says given that the reaction is SN1 or E1 or E2 or SN2, I forgot my list, okay, draw the result. Okay? And so what he's trying to do there is help kind of convince you, this is the lane you're in, make sure you draw the result of that lane. Okay? The benefit of doing it this way is that we can use any reagent we want, and we can say, just do it. Make it SN2. But it wants to go SN1. I don't care. Make it SN2. Okay? It allows us to get a better conceptual understanding of each of those individual mechanisms. Once we have an understanding of those mechanisms, then Cardi says, well, actually, you should evaluate the reagents a little bit more carefully than just saying, oh, it does it. Okay? And you should take a step back and say, well, what are those component pieces? Okay? So when we're thinking about that, we need to be aware of some of the kind of components. So considerations. Do you have carbocations? You should be thinking rearrangements. Acids and bases. You might see some stuff from a leveling effect. Okay? In a strongly basic reaction, don't form a strong acid. What charge would you expect to see in a strongly basic reaction?
Negative.
Why should you see a strongly negative charge in a basic reaction?
See if we get.
Shh. Name a base.
Hydroxide.
Sodium hydroxide. What is the charge on hydroxide? Negative. So what charge should you see in a basic reaction? Negative, because that's what makes it a base. What charge should never show up in a basic reaction? A positive, because when do we see positives? With acids. Okay? So making those kind of simple statements can help us kind of tweak out our mechanism as we move through it. Okay? Intramolecular reactions, you should avoid them unless you are forced to do so. These are usually pretty tricky and rare. You will be forced to do them. Okay? It's again a favorite of the ACS because it is a tricky reaction. Okay? It tends to confuse students. Okay? And one of the reasons it tends to confuse students is again the focus. When you look at a structure, where do you look? Okay? Outermost part. Okay? And I would agree kind of along those lines. You're going to look at the entire structure. No, it's not where you should look. Inside the structure, no.
You should look where the reaction happens.
Where the reaction happens. Where's the reaction going to happen?
If it's an elimination, near a pylon. Or where
Too many conditionals. Okay, leaving group kind of helps, but then you know what a leaving group is.
We're looking at the most reactive atom.
Why would an atom be reactive?
So the most electronic.
Charge. Okay, why would it be charged? Because it's electronegative. So when you look at a structure, you should find the most electronegative atom and keep your focus there. Ow. Oh.
you just do to yourself?
I have no idea.
Oh, I thought that was.
No, that was not part of it.
Oh, man, you see flipping this off now.
Yes. Wow. Oh, that's really unpleasant. You need to be looking for those most polar atoms and focus on how those electrons are being drawn one direction or another. That's going to generate partial charges. Once you've established partial charges, you can then start to react those partial charges. A partial positive should react with a partial negative. One of the benefits that you get in this first section is that, is that we really only have one partial positive and one partial negative. We don't really get more than that. Right? The intramolecular reactions are a little bit different in that you can get multiples of each of those. Okay? So we do have to be a little bit careful when we look at our reactivity. Find that most electronegative, look at that displacement of those charges, okay? And then you can pretty much do what with the rest of the structure? Delete it. The only reason it's there is to confuse you, is to make that problem look different than the basic core elements of all the other reactions. So stop hyper-focusing on the stuff that isn't happening. Okay? So we find that most reactive, and then I would recommend expand outwards just a little bit to include the next 2 or 3 atoms outside it. Once you've looked at those 2 or 3 atoms, now start to do comparisons and look at your reactivity. Okay? If you need to go further, but for the most part, keep it very, very centralized. Okay? Okay? With our substitution and elimination reactions, the basic components, substrate, leaving group, nucleophile / base. Why slash? Both a nucleophile and a base are ultimately the same thing. They are both donating electrons. Their only difference comes down to what they're donating electrons to, and that becomes the challenge. Okay? And then your solvent. Okay? Nearly all questions in this section are boiling down to looking at one of those pieces and saying which one is standing out as the most important. Because once we've identified which one stands out as our reaction, well, now we know the mechanism. And once we know the mechanism, we just proceed forward and do it. Right? We follow those rules that we learned in Chapter 8, and we just do the reaction. The end result, we have to evaluate. Do we have cis-trans? Do we have chirality? Do I have to be concerned about those pieces? Right? So this is where the videos, supplemental videos, popped up. Right? So we have substrate classifications. I would kind of like to go fast through these because in theory I talked about them in detail in the videos. Right? Does that make sense? Okay. So, zero, primary, secondary, tertiary, no questions? Okay. Cation stability. Which one's the most stable? Tertiary. Why? More electrons to stabilize it. Okay. How do we apply this out to these alkyl halides? Okay. So notice in this case I'm telling you in the second part, react according to SN1. Okay. So we could categorize each of these. That first one would be primary. The next one would be? Last one would be? Why is the second one different color? Because not primary, that's a possible suggestion. I didn't realize that until after I asked the question. No, that's not why I changed it. The secondary is connected to 2 carbons, and what's not shown very well is that all of those carbons are sp3 hybridized. Is that the case in the second one? No. That one doesn't really classify under the primary, secondary, tertiary rules. Right? Because we could go back through with these cations and just add a leaving group. Okay? And these are going to maintain, whoa, big zoom in, our primary, secondary classifications. Okay? And so the important part that I want to address here is that if we look at the secondary, where is it? Here, that center carbon is sp3 hybridized. With the one that you called secondary, is it sp3 hybridized? No, it's sp2. That carbon does not get called secondary, it gets called sp2. Okay? That is an sp2 position. You will sometimes hear that referred to as vinylic. Okay? It is different than allylic, and we'll see allylic here in a second. Okay? Why would the chemistry all of a sudden change that I need to use a different name? Yes. What's the hybridization of our carbon? sp3. What's the difference between sp3 and sp2? Less S character, which means?
More electronegativity.
Electronegativity. Why is that going to matter? What is our leaving group trying to do? Leave with electrons. If an sp2 is more electronegative, it's harder for it to leave. So there's already an argument that the sp2 should be less reactive than any of these because it has a higher electronegativity. Okay? So, let's move to the next one. It says, how should they react according to an SN1? When I say SN1, you say carbocation. Okay? So, would I expect a primary carbocation to form? No. Do I have a primary carbocation? Those of you in lab should be able to answer this question because that structure looks kind of familiar, doesn't it? Because you all did the post-lab already. What is special about that structure? It has resonance. Why is the tertiary more stable than the secondary? There's no delocalization when we look at tertiary versus secondary. Why is tertiary more stable than secondary? There's more electrons around, near. What is happening in resonance? We are literally moving electrons. Which do you think is going to stabilize more? Just having more electrons around or actually moving electrons to it? Actually moving electrons to it. This isn't primary. This is primary. And depending on how you want to reference it, I usually do primary plus, okay, or primary plus resonance. What does that do to the stability of the carbocation? Increases it exceedingly. Okay? So much so that a primary plus resonance roughly equates to a tertiary. Okay? And depending on where you look and who you talk to and what study you're using to compare those stabilities, they can kind of oscillate back and forth. Sometimes you'll see the tertiary be more stable than the primary with resonance. Sometimes you'll see the primary with resonance more stable than the tertiary. It all just kind of depends on luck of the draw. Okay? At least at this stage. When we moved to the sp2, well, we said the sp2 was more electronegative than all of these, right? Okay. Does the zeroary form in SN1? No. If the zeroary doesn't form, what's going to happen here with the sp2? It is also not going to happen. That reaction doesn't even get out of the gates. Okay. The carbocation that would be formed there, if we were to say form it, what can you tell me about the hybridization of that carbon? It is sp. You might say, well, what about the hydrogen? There is no other hydrogen there. Remember where it came from. It only has two groups of electrons. It is sp hybridized. What is the bond angle for an sp atom? 180 degrees. Am I going to be able to get easily 180 degrees in this structure? No, that's going to start to really piss off the rest of the bond angles. Okay? So that becomes a problem. Add to that, where's that carbocation? Okay? Said another way, the pi system, those p orbitals are coming in and out of the plane. So there's p orbitals all the way there. If there's a carbocation, there must be another p orbital. Where is it? It has to be perpendicular to the p orbital coming in and out of the plane. Okay? Which means it could potentially be sitting somewhere like this. It could be sitting somewhere like this. Both of those are going to be weird systems. We've got a p orbital going into the ring. That's not happy. Okay? Tangent to the ring. Virtually everything about that carbocation screams, don't make me do this. Okay? Which is why, what happens? Nothing. This reaction heavily goes backwards to your starting material. We could call this a no reaction. Okay? The bottom one looks like primary again, but what's right next to it? We have that potential for resonance again. Whoops. Whoops. Keep doing it. So we can get resonance outwards, yeah? Everybody agree?
Yes.
Okay. So now what I want you to do is take a look at that top structure and the bottom structure. Do those look kind of similar?
A little bit.
Yeah, those are effectively the exact same thing, right? Okay. One involves resonance on just a standalone double bond. Another one involves resonance from an aromatic ring. Is an aromatic ring different from an alkene?
Yes.
How do you know that?
Because there's more carbons.
This one has more carbons, and I'm going to argue it has the exact same reactivity as the top one now. So no, I don't accept more carbons being different. Is an aromatic ring different from an alkene?
Yes.
Yes. How do we know?
It's an aromatic ring, not an alkene.
We literally give them different names. So yes, they are different. There's our easy answer. Of course, that's going to be followed with why?
Because they're ringed up. They have extra piles.
What is that ring system going to do to make it different?
Spirals around.
Those electrons can now constantly cycle around within the ring. For an alkene, where can the electrons go? They can really just bounce back and forth wherever there's a pi system. I can only go back and forth. Okay, walking back and forth versus in circles. Most people, when you go out jogging, do you enjoy running around in a circle or just back and forth?
Back and forth.
Okay? We tend to prefer those larger distances to see more exciting things. Okay, same deal with hikes, right? You like hikes that go around in circles, not back and forth? Okay? Same general idea. Okay, so because of that, we call these structures slightly different, or this resonance effect slightly different, and somebody started to suggest it. Top one is, I think it was you. Yeah. The top one is allylic, and the bottom one is benzylic. Not to be confused with benzyl, phenyl, or a multitude of other benz type names, okay, which you'll probably see later on. Okay, so allylic and benzylic can be referenced. Ultimately, all we're saying is that those have resonance. Does resonance matter?
Yeah.
Yes, it is huge. You need to always be considering resonance when we think about stability. Okay, so reactivity summary. Okay, tertiary plus resonance, better than secondary plus resonance, all that fun stuff. Okay, leaving group. Okay, if I was to have a nucleophile attack this structure, where is it going to attack? Okay, long pauses, generally a bad idea at this stage. Okay, when we look at this structure, where do we want to look? The most reactive atoms, or most electronegative. I see chlorine, I see bromine, I see oxygen. What are they all connected to? That carbon. So all of those atoms, chlorine, bromine, oxygen, are all partially negative because they're pulling electrons from the carbon, making the carbon very partially positive. Where's my reactivity? In the carbon. The nucleophile is going to come in and attack. That carbon will act as an electrophile. As an electrophile, it accepts more electrons, but at the same time, it already has its octet satisfied. Okay? So as it accepts more electrons, what must it also do? Get rid of electrons. Okay? It's going to have to kick out electrons to something. What could it kick out? Since I already heard it, we could kick out the hydrogen. We could kick out the oxygen with the hydrogen. We could kick out the bromine. We could kick out the chlorine. That in and of itself is kind of misleading. What should we be adding to those structures? Step back from the charges, go to the electrons. Remember, they're leaving with those extra electrons. Okay? Because they have those extra electrons, what happens to them, Raph? They are all negatively charged. Which of those is the most stable? How do you know the bromide is the most stable?
Because it's larger, so it will be more stable with the negative charge.
Okay. So for those you didn't hear, she said it's largest. Okay. We start with charge. Are they all charged?
Yes.
Yes. So what do you move to? Size. Okay. Oh, interesting. That sounds kind of familiar. What follows size? Electronegativity, followed by resonance, followed by induction. Should you be using those rules to evaluate all of your chemistry? Yes. Okay. They're there for a reason. They will help you go through to decide this. Bromide being the most stable is going to be the most likely leaving group. What would be the least? Why the hydrogen? Okay. It is the smallest of them, least able to stabilize that charge. Okay. Make sense?
Yes.
Okay. You're just following those charges. When we look at a structure, though, sometimes, we're going to do this. Sometimes we may see a structure, and it may not be inherently obvious to us. This one hopefully was. So let's make a little bit of an adjustment here. How about now? What's our best leaving group? The oxygen. So we go through and we run our reaction. What do we get? I don't care about stereochemistry for those of you who are worried about that. I get OH minus. What else do I get? And then whatever that nuke is. Did we say hydroxide was a good leaving group? It's a bad leaving group. Your leaving group, if we think about our reactions, when the leaving group leaves, it should exist on its own and be stable. What do I mean by stable? I recommend a face test. Okay? By a face test, take whatever you just left from the structure and splash it in your face. Are you going to be upset? Hydroxide is a strong base. I'm going to be exceedingly upset. If you don't want to use your face, you can use my face. That's fine. I'm still going to be exceedingly upset. Okay? All sorts of litigation, lawsuits, fun stuff like that. Okay? That's not good. If that's not good, what happens to that mechanistic step? It doesn't happen. Okay? So when we talk about leaving group ability, it has to be a good leaving group. If it is not a good leaving group, it can't leave the structure. How could I make OH into a good leaving group? Add a hydrogen to it. Okay? So instead of adding a strong nucleophile, what do I need to add? Okay? I need to add something that is going to put a hydrogen onto that structure. So I could add HCl, HBr. This now gives me a strong acid-base reaction. And I end up with a positive oxygen. Does oxygen want to be positively charged? So what does it want to do? Leave the structure. Now my nucleophile could come in, attack, kick out the leaving group, and I would now have H2O. Am I okay if, or would there be less lawsuits if you splashed H2O in my face? Yeah. Okay, I would probably just laugh it off as long as it wasn't in lab. In lab, I'm going to have a few larger issues. Okay? Kind of makes sense? So leaving groups, primarily what we're focused on is just our halogens as leaving groups, but be aware we can have other leaving groups. Make sure they're stable. How do you know they're stable? What do you need to think about? Charge, size, electronegativity, resonance, induction. Okay? If you aren't sick of that yet, you haven't been listening. Okay? And I will repeat it probably twice more this class period. Okay? We have to be constantly looking back at those. Okay? So, traits of leaving groups, electron withdrawing. That sounds kind of like electronegative. Okay? Weakest base once it's left. Okay? Polarizable. Okay? Those are all categories of the charge, size, electronegativity, resonance, and induction. Okay? So when we look at our leaving groups, they've got them ranked out kind of nicely for you. You could look at those. I don't think I would memorize those, but it gives you an idea on what's going on behind that. Kind of makes sense? Okay. Solvent classifications. These are a bit nasty, okay? And they're almost always hidden, okay? If you see a solvent listed, it is probably because they are asking you a question that requires you to think about the solvent, okay? In this chapter, or in this sequence, that means you're doing what? I know, a big, vague question. If we list the solvent, when is it important? It is important not necessarily for SN1, SN2, but right path, substitution. Our eliminations tend to be misleading, so don't use the solvent to evaluate your eliminations. Do it for your substitutions. Okay? Your primary goal for your solvent is to get everything into the same place so it can react. That's its goal. Okay? Secondary is it can stabilize or destabilize reagents and intermediates. Okay? This is why when we think about the solvent and we look at, let's see. Yeah, okay, I didn't put it there. When we think back to our SN1, what do you tell me for SN1? You tell me carbocation. Okay? And that's because when I look at the energy diagram for our carbocation, I get something like this. There's my carbocation, there's my reagent. For this reaction to go faster, what do I have to do? Lower the activation barrier. How can I lower that? If that carbocation becomes more stable, my activation barrier drops. How do I make the carbocation more stable? How do I stabilize a positive charge? I need to give it electrons. Okay? I want this to be a partial negative. Why not a formal negative? We don't have a carbocation. That's a possibility. If we're talking about the solvent, do we want the solvent to act as our nucleophile? And that's where we run into kind of a borderline situation. Our SN1s, almost always the solvent is the nucleophile, but not always. Okay? Typically, we want the solvent there to stabilize, not react. Okay? So that's why we would stick to a partial negative. Okay? Where do I get the largest partial negative from my solvents? I just advanced a whole bunch of slides through, and there were some terms that popped up that we would use to classify solvents that we talked about in Unit 1. Protic, aprotic, nonpolar, polar, and nonpolar. And we broke those down into 3 primary categories. Those were, we could get away with just calling it protic because protic will always be polar. Okay, the next one, polar as well, but now aprotic. And the last one, nonpolar. In the case of the carbocation, I want the largest partial negative. Where do I get the largest partial negative? From a nonpolar solvent? No. I want a polar solvent, but I want the largest partial negative. What's going to generate the largest difference in charge? A hydrogen bonding solvent, that's a protic solvent. So in the case of the SN1, the solvent I want is protic. How do I know it's protic? Hydrogen bonding. Okay? Which we could also add arfon. Okay? We would have to see those pieces in our structure. Make sense? When I say SN2, what do you say? Backside attack. Okay? If I look at the backside, how would the solvent change my ability to get back there? That's a pretty hard question. I would argue it doesn't really. Okay? So let's just push all the way. Let's just say it matches SN1. We go with a protic solvent. What does a protic solvent supply? Hydrogen bonded to an electronegative atom, right? What charge is that hydrogen? Partially positive. Where is that hydrogen found? In the solvent, in the solution. Where in the solution? When we mix reagents with a solvent, what's the concentration of the solvent in comparison to all our reagents? It's a lot. Okay, it's a huge concentration of solvent, which means, what's the concentration of my H+? There's a ton of H+. What's the concentration of my little partial positive in there?
A lot less.
A lot less. Where's the nucleophile going to go? It's going to go to the partial positive hydrogen. Why? Why is the oxygen, the negative trying to cancel out that negative? Because it's negative. We're going to try and kill it as fast as possible. How do we kill it? Positive hydrogens that are readily available. So is a protic solvent going to be a good option? No, because it's now going to outcompete. The solvent will compete with our substrate for the nucleophile, which means the rate of our reaction goes to the floor. Right? We're effectively removing the concentration of nucleophile. So that's a bad solvent choice. Okay? But what if, instead of it being a hydrogen, I say made it a carbon? Is that now still going to be a large partial positive? Yeah. It's still going to be there in a high concentration, but where is that partial positive? It's in the middle of the solvent molecule. Because it's now in the middle of the solvent molecule, what happens to the ability for the nucleophile to react with it? A lot less. So it makes it less likely for the nucleophile to be competing with the solvent, and we're going to get our nucleophile attacking our substrate. Do we want it to be polar at all?
Yes.
Yes. Why? The nucleophile for an SN2 is strong, charged. Your substrate is not tertiary. It's typically organic, weak intermolecular forces, non-polar. What are the odds I would be able to get a solvent or be able to take my exceptionally polar substance and get it to react with a non-polar substance? Very, very limited. So what do I need? I need a solvent to help bring them together. That solvent needs to have the properties of both the non-polar and the polar, which would be in a spectrum of 3 different solvent categories. Right in the middle, which would be our polar aprotic. Right, so on our SN2, we want that polar aprotic. Okay? So in our classifications, when you look at a structure, you should be able to nail down those classifications pretty quickly. Okay? And I would argue we've already done this. We did this back in Unit 1. So you should be kind of rock stars at just being able to identify that. The next step is being able to look at it and say, that one's this mechanism, that one's this mechanism. Okay? Benzene. Okay? I'll accept that. DMSO. Polar aprotic. You're actually answering the question I wanted you to answer, Donald, but not yet. Methanol. Polar protic. DCM. Polar aprotic. Acetic acid. Polar protic. So the initial question that I was asking, because you guys should be really, really fast at that, the question I was asking is what mechanism? So let's start right to left. Acetic acid. SN1. Why? Because it's protic. DCM. SN2. Methanol. SN1. DMSO. SN2. Benzene. Not really an appropriate category for substitution reactions. As a nonpolar solvent, it's not going to do a good job of actually bringing those reagents near each other. Okay? Benzene is actually just bad. Let's just say that. A bad choice. Yes?
Can you use it for an E1 since it's only using a weak acid?
Can you use it for an E1? In an E1, what is your very first step? Formation of a carbocation. Is benzene going to stabilize the carbocation? No. Okay? So, when we think about SN1, SN2, E1, E2, it's important to remember what those symbols mean. E means? Elimination. Which means?
Removing the hydrogen.
pi bond formation through the removal of a hydrogen in a leaving group. S means?
Substitution.
N means?
Nucleophile.
What do you expect to see in an SN mechanism?
A nucleophile.
Substitution with a nucleophile. Hey, it's right there in the name. Okay, 1 means?
A one rate order for the
Okay.
reaction.
This almost always trips people up. Okay? So there's a variety of things that you can tie to that 1 in SN1 or E1. One option was saying 2-step. I'm going to say that's kind of confusing, but if you got it, that's fine. Okay? The other one, it's unimolecular. That's probably equally confusing. That's a bunch of letters that no one can even actually say together.
Yeah.
If I say
Okay.
the limiting step is rate 1.
What are we saying with unimolecular? There is one species in the rate law. Okay? Which is also equally confusing because how many of you liked 152? There we go. Okay? So that's why the 1s and the 2s can be confusing for people. Because what they're referencing is a class that almost everybody roundly dislikes. Okay? I said almost. What's the 2 mean?
Second rate order.
So 1 step.
Okay? So we could memorize 1 step. Okay? It ultimately means there's 2 things in the rate law. Okay? So make sure you've got those terms kind of tied to each other. Okay, we just walked through all those questions, so we're going to skip that. The nucleophiles as electron donors, okay, ultimately comes from their definitions. Okay, we've got those identified up at the top, which is kind of fantastic, so we'll deal with those. You should already be good at those. The harder rankings come down here. Okay, size of nucleophiles becomes very, very challenging to deal with. Okay, and the reason it becomes challenging is because there's a huge solvent dependence. Right? If you are polar protic, a bigger molecule or a bigger nucleophile tends to be more nucleophilic. If you are polar aprotic, a smaller nucleophile is more nucleophilic. It switches. What the hell? Okay. Well, the reason it switches has to do with how the solvent is interacting with the nucleophile. And that is an exceptionally challenging thing to deal with. Okay? It is one that when I see it personally as a question, I usually leave it alone because I figure odds are I'm going to screw it up and I'll come back to it later. Maybe. Okay? If there's no solvent, bigger is more nucleophilic. Okay? So you have to be a little bit careful when ranking nucleophiles to see, is there some kind of secondary categorization maybe with the solvent? Okay? It tends to be a much rarer question to ask, okay, even for the ACS. Yes?
Is that a size issue for the polar protic?
This is all size.
Okay. Looks like the smaller one can get inside of a protic or any protic.
No, I'll show you that in a second.
Okay.
Okay? One that's not as hard but much more important, which we've also talked about in class, is that bottom one. Okay? Steric hindrance. Less atoms is more nucleophilic. Right? Because what is the nucleophile reacting with? An electrophile, which is inside the atom. To get inside the atom, you have to use a smaller molecule. Okay? They didn't try and blow up the Death Star with a Star Destroyer. Okay? Because the Star Destroyer is too big to get into the little hole. Sorry, I'm just going to move on. Nucleophiles and solvents. So let's go ahead and take a look at this. Okay, what we've got in the top case is our polar protic. In the bottom case, we've got our aprotic. Okay? In the protic, what did we say? Which nucleophile did we want?
Bigger.
Protic, we wanted bigger. Okay? Why bigger? In a protic environment, we're looking at a hydrogen bonding interaction. Which of these has a stronger hydrogen bonding interaction, chlorine or bromine? The hydrogen bonding interaction is due to what? A difference in electronegativity. Which of these is going to have a stronger interaction with water? Chlorine, because chlorine is more electronegative than bromine. Okay? So what does that do? The interactions now between the solvent and the nucleophile are so strong in comparison to the bromide, that's going to slow that rate. Bromide becomes a better nucleophile because it has a weaker interaction with the solvent. And for the nucleophile to react, what must it do?
React with the molecule.
React with the molecule, not the solvent. Okay? When we move to an aprotic system, what happens? Well, in the aprotic system, it switches around. Well, why does it switch it around? Okay? Those molecules are now larger typically in the aprotic system, which means I can get fewer molecules around a smaller molecule. Fewer molecules around it means fewer interactions that I have to break to get the nucleophile to react with the substrate. Okay? It is a difficult one to process, but that's ultimately how it works. When you remove the solvent altogether, we're looking at this concept of polarizability. How much can you shift the electrons one direction versus another? If it's a small molecule, you can't really shift them. Okay? So it becomes less reactive. The larger molecules become more nucleophilic because you can shift those electrons one direction a little bit cleaner to be able to do the reaction better. Okay? The next big one is our size. Nucleophiles donate electrons to things other than hydrogen. Bases go to hydrogen. So this is why sterics play a role. In this structure, I have two reactive things. What are my two reactive things?
Bromine and oxygen.
The bromine is not reactive. Okay? I will accept the oxygen as being reactive. Why is the oxygen reactive? It has that negative charge. Okay? It is now willing to share those electrons. The bromine, I can understand why you would zoom in there, because we're like, oh, bromine's electronegative. That must be a reactive site. But remember what I said. Find the electronegative and then do what? Look at the immediate chemical environment around it. Okay, so I need to be bringing in the carbons around it. The next layer behind this, which is more reactive? My bromine substrate or the oxygen? The oxygen, because it is charged as a negative, which means it needs to find a positive. Is the bromine a good positive? No. What would be a good positive? That carbon, where the bromine is connected, would be a fantastic positive. And we would run what kind of a reaction? A substitution. Okay? Where else is there a reactive position, potentially highlighted by being anti to that leaving group? The hydrogen down here. There are two positive locations. So we zoom in to where the electronegative is, and then we slowly step out to see where there's reactivities. Okay? In a larger question, you might also have to consider the hydrogen here and the hydrogen here. Okay? And for that matter, the hydrogen out here. Why must those hydrogens also be taken into consideration? Those are all beta hydrogens. All of them should be evaluated. Okay? In this case, all we're trying to do is to zero in on the blue positions. Okay? For this negative to attack, which is easier to get to, our blue hydrogen or the blue carbon? The blue hydrogen. And we would get an elimination. Okay? Which would be a pi bond, which would be higher in energy. Is there something that could potentially produce something lower in energy than that pi bond? A substitution. If that oxygen can get in and attack the carbon. Can it? If it's small enough, why not? What if instead I switched to this guy? This now has a whole bunch of methyls on the outside. That's going to be a lot harder for that negative oxygen to get in to react with that carbon. And what we're referencing now is the steric hindrance. Okay? And that structure will primarily act only as a base. This is how sterics affects our reactivity between nucleophiles and bases. They're both doing the same thing, but from a slightly different perspective, and we have to be careful with applying their definitions appropriately. Make sense? Okay. That structure, what do you think? Sometimes it can help with lone pairs. Sometimes it can help with resonance. I'm not even going to attempt to draw that stupid 7-membered ring. We've got a strong negative, which means it could act as a nucleophile or a base. Which do you think? Nucleophile or base? Base because that's too big. Okay. That species is either DBN or DBU. Sometimes you'll see reference to those. I don't remember which one it is. Both of those letter sequences reference bases, I believe. Okay. For nucleophiles, do we have things that can only act as nucleophiles? Sort of. Okay. And that's where it becomes kind of challenging. OR, kind of like OH minus. Same thing. They're both negatively charged, but they're both small, which means as being small, they could act as a nucleophile or a base. Okay? Acetylide, small, nucleophile or a base. Okay, so almost all small things can act as both a nucleophile and as a base. We have to be a little bit careful with them. There is one kind of pseudo category that we could memorize as an exception to that. Our halides will act exclusively as nucleophiles. They will not act as bases because their conjugate acid, if they acted as a base, was a strong acid, which by definition completely dissociate. So they wouldn't act as bases. Okay. The solvent effects, we just addressed all those. Okay. Acid-base mechanistic steps that could be bad. If we go through and run this reaction in both cases, okay, it looks like we're running what kind of reaction? Beginning to end is a substitution. Beginning to end is a substitution. Okay. We could go through and say, well, this attacks here, kicks that out. I would have this as an intermediate. Does the oxygen want to be positive? No, so what happens? I've got the OH minus that can potentially come in, remove the hydrogen, stabilize it, and I get my product, yes? Okay. In that question, I have now drawn a mechanism. I've drawn this as 2 steps. Acid-base and substitution. In particular, acid-base and then SN2. Other way around. SN2, then acid-base. Is that mechanism valid?
For an SN2? No.
What is wrong with this mechanism?
It's not final molecular.
No, I cannot put this all on one. So in an SN2, some people go, well, an SN2 is only 1 step. This is done in 2, so it can't be SN2. The SN2 says the SN2 part of the mechanism, just the substitution, happens in 1 step. If we take a look at that first step, that was an SN2. The next step is an acid-base. Did I call the whole reaction an SN2? No, I called the whole reaction substitution. Okay? So the number of steps saying, well, this is an SN2 is wrong. You're making a false statement. You're layering a mechanism title onto a reaction title. The reaction title is substitution. Everything about that, as shown, is still valid as an SN2 and an acid base. So again, the question, is that a valid mechanistic step? Or a mechanism for this?
No. It takes place in 2 steps.
No. The 2 steps has nothing to do with it. You're wrong. You're referencing, again, mechanism versus reaction.
I mean, you only have 1 box.
Today's Monday.
I could be reading this wrong, but what I'm seeing is that I have the box, and so I can only do 1 thing, and then I would need another box to create a new set of.
No. I don't know where you're getting that from, but that's false.
Okay.
What is your reaction condition? What is sodium hydroxide or potassium hydroxide?
Basics.
A strong base. And what can never form in a strongly basic environment? An acid. Can you tell me what that structure in the middle is doing? An acid. In particular, what kind of acid? That would be a strong acid. I just formed a strong acid in a basic environment. Is this mechanism valid? No. How do we fix it? Do the acid base first. Now you have a valid mechanism. You have to be cognizant of the conditions you're in. Don't form strong acids in a basic environment. Don't form strong bases in an acidic environment. Evaluate the pieces as you move through. Think about them critically as you advance. Okay? Yes?
So this one you did HOH instead of KOH, right? But if you were...
No, this one is hydroxide. It's KOH. That last step just says KOH. Okay? All those are reagents. Those reagents were placed in such a way to make you kind of freak out and potentially draw things incorrectly. Okay? But those aren't saying that those are involved in those steps necessarily.
I was just saying
They're just there.
oh, okay.
Okay? So in the bottom one, what does it look like happens? And because I heard someone whisper about it, whoops, wrong eraser. One of the things that we could go through to do when we evaluate a mechanism is to look for the most reactive thing. Okay, so if we're asked to provide a mechanism, what you should be doing is not going, oh, this is substitution, I'm going to do SN1. What told you need to do SN1? Okay, what you should do is look at your reagents and say, that I don't want splashed in my face. I'm going to fix that. So when you look at that starting material, what do you not want splashed in your face? KOH, because that's a strong base. That is potassium ion with hydroxide ion. Because that's an ionic bond, I can delete that. That is a negative charge. What should I do to stabilize that negative charge? Find a positive. Where's there a positive? Whoa, that's an eraser. I can go for that hydrogen. Why go for that hydrogen and not say that carbon? Why is that step not a good one? Where are you trying to get? Where are you trying to get? Should the oxygen attach to the methyl in that way? Would it get you with the benzene ring? No. Okay? When you're being asked to draw a mechanism, you're given beginning and ending. Use that information to your advantage. We have to go ahead and stop. Okay? I am going to point out we've got really intramolecular, a little bit of alkyne stuff. Okay? And then what it gets down to is that summary at the end, those last 10 slides. Those last 10 slides have a lot of very important summary information on them. Notice complications, rearrangements are possible for the SN or the SN1. You need to review those. And if you look through those and you're like, I know what all those terms are, you're probably okay. If you look through those and you're like, what the hell is polar protic? You should get that fixed. Right? Because these summary slides are ultimately what's going to drive almost all of your reactions. Okay? So if you've got those nailed down, you should be good. Memorizing it isn't necessarily helpful, so please be careful on that front.